Hello everyone. So the round just wrapped up, and yeah, let's talk about the round. So basically, I thought the problem difficulties were kind of weird this time. I thought C was really hard, but I also realized later that I messed it up a bit, and I messed it up a bit, and I could have made it a lot simpler. But I thought C was quite hard. This is like a decently big jump, but I guess a lot of people spent time on C and ended up getting it eventually. This gap between B and C was a lot bigger at the beginning of the contest. And then, yeah, I definitely thought E was harder than F. F seemed like a relatively straightforward DP to me, but I mean, I think that's also reflected in the solve count. So, and yeah, just overall pretty hard as a contest. I think, even A was a pretty hard div to A, and I guess I'm kind of surprised by number of solves on B being that close to A, but then, yeah, starting from B to C to D, you get some pretty big drop-offs. Also, we did have a hydrate. Also, I saw Mango Lassie said D was the hardest problem, which is kind of funny. Yeah, I guess D is like, if you just miss the solution, there's not really much else. So you just kind of have to make the right observation, and then you just get it. Yeah, I mean, for me personally, I would say the problem order was something like A was the easiest, and then B, and then and then F actually, and then D, and then some mix of C and E. So yeah, also a weird order for me. I mean, if you look at my, I guess system testing is kind of, yeah, I'll just look at my submissions. Yeah, if you just look at my solve times, like for A, I took 1 minute, and then for C, took like, for B it was like 6 minutes, for C it was like 14 minutes, and meanwhile F only took me about 6 minutes, so just kind of funny stuff going on there. But anyway, yeah, while the sys tests are running, we can get into the problems and talk about the ideas. Is it saying stream is over on Codeforces? Oh, let me fix that. When I started, it wasn't saying that, so that's kind of weird. Okay, let me just fix that. Okay, should be up now. Yeah, so today I only have about an hour, so I'll try to go through the ideas a little bit quicker. So yeah, let's start with A. So problem A, you've got two positive integers A and B, and you can do two operations. One is take A and divide it by B, and also take the floor. The other thing you can do is increase B by 1, and then you want to know the minimum number of operations to make A equals 0. So there's a couple key insights to solve this problem. Oh, and then also you need to solve 100 test cases, and A and B are up to 10 to the 9th. So that's pretty big. So yeah, a couple observations you need to make to solve this problem. The first one is that if you do any of these B increments, you should just do them at the beginning. Because just to give kind of an example, let's say A equals 10th to the 9th, and then B equals like 3. Let's say we do Mux FD, thank you for the rate. Yeah, so let's say you do you do the divide, and then you do B++, and then you do the divide again, you do B++, and you divide again. So then what you kind of did was you divided by B, and then you divided by B+1, and then you divided by B+2. But if you just rearrange these, so all the B++'s come first, then you'll end up doing this instead, which is better, right? This is definitely going to be no bigger than this number. And so yeah, so we should rearrange the b increments to be at the beginning. And then once we do that, we'll just divide over and over until we hit a equals 0. One thing that's a little tricky is when b equals 1, this is actually not possible to get to a equals 0. So we have to kind of watch out for that as a special case. But yeah, otherwise we can just think about, okay, let's loop over the number of times we increment b and then keep dividing. And the question then is, how many times should we increment? Like how far should the loop go? And you can just show that, one example is like, you can show that, you know, you shouldn't go more than like 20-ish times. You can just pick a number like between 20 and 30 and try to show that that is an upper bound. One reason is, so b starts as at least 1. If we increment it, let's say 4 times, we'll get to 5. And then if we divide even 10 to the 9th, if we divide that by 5, you know, let's say 16 times, or we don't even need 16, we need like 13, I guess. 13 times is enough to get it down to 0 in this case. So yeah, so there's no reason we need to do any more than like 20 increases for sure. And you can even show 10 or tighter bounds. But basically the code ends up looking like this. So I just loop over how many times we add 1 to b. And wait a second. Oh yeah, okay. And yeah, I just actually increment b here, and then I make sure b is greater than 1 before doing this, otherwise it'll loop forever. And then just start with a, divide by b over and over, and then take that as an option. And so this is really fast. This is like 10 times log of a. So the runtime is super fast. Another hydrate. Oh, sure. You could do all of the. There's like 2 to the 20 options. Someone used BFS. Yeah, I guess there are funny things you can do here. Why is loop 10 times? So that's what I was describing, where you don't need to do more than 10 of these. Well, I showed 20. 20 is definitely easy to show because by the time you do 20 of these, you could have already finished. So yeah, so we don't want to do more of these than the actual answer, right? And we can show the actual answer is less than 20 in all cases. And that's why we don't want to do more than 20. In this code, it does up to 10, but yeah, it doesn't really matter. 10 is fine, 20 is fine. Oh, some solutions are failing on system tests. That is interesting. This is a failed B. Yeah, I'm curious if there was anything in my room that failed, because then I could have gotten some hack points, but looks like nothing yet. Anyway, okay, so that was a YaxZH said increasing B square root 8 times, is that enough? Yeah, I actually had someone in my room who did it 1,000,000 times, and I was like, huh, is that gonna TLE? And so I tried it out, but it's basically about 100 million divisions, which is actually fine. It ran in 0.3 seconds. Okay, so let's move to B. Just keep it moving. Basically for B, there is a property called k-similar, and then 2 arrays are k-similar if they're strictly increasing, they have the same length, and every value in the array is between 1 and k inclusive, and then there's one position exactly where they're different. So you're given a strictly increasing array, you're given k, you're given a bunch of queries. For each query, you're basically trying to find the number of arrays that are k-similar to this subarray. Okay, so yeah, basically the idea for this is if you want to make something that's k-similar to this, we have to pick exactly one position and then change the value. And we can think about how many different ways we can change each of the values. So let's take a subarray. Let's say k equals 10. We have a subarray that's like 2, 4, 7, 8. And then let's take this 7 and let's think about, make this bigger. Okay, let's think about how many values we can change the 7 to. Well, it still has to be between 4 and 8 strictly, so the only options are 5, 6, 7. And then 7's not an option because that would mean we're not changing the number. So we have 2 options. And the actual count, you can just get it as like 8 minus 4 minus 2. So it's like, it's AI plus 1 minus AI minus 1 minus 2. And that's the number of options for general numbers. Now, there is a special case for the first value and the last value in the array. So if we're trying to change this 2, then we have to be less than 4, but then we don't have any AI minus 1. We don't have this thing. So basically the options are, it has to be at least 1. So the options are 1, 2, 3, and then we don't have 2. So there's 1 and 3. So for that case, it's like A1 minus 2. And then, for the 8 case, it's something similar. It's 8, 9, 10, but we don't have 8. So separate these a bit. And so it's just K minus I guess, I minus 1, where I is the last one. Minus 1. Let me check. Yeah, that looks good. So yeah, basically these are the kind of options for each element of the subarray. And so the thing is, we want to add these up for the whole subarray. So we could implement it as kind of a loop and go through and add things up. But because that's too slow, we need to speed it up. So what we do is we pre-compute all of the inner values. So all the values that are not Li and are not Ri, we're gonna take a sum of those in O of 1 time, because we're just gonna pre-compute this value, and that's what this is right here. So choices I is the number of choices for AI, assuming that it's not the left end and it's not the right end. And then this is the prefix sum table of that array. And so this lets us do a sum in O of 1. We just do the prefix sum of the right end minus the prefix sum of the left end. Let me just check chat. Yeah, hello 1, 2, 3. Yeah, the idea comes faster than A, but the implementation is harder. That seems reasonable. Yeah. Crow is asking, how many operations can you do in 1 second? So that's kind of a tricky question to answer, because the answer is really, it depends. I mean, it depends on what type of operation you're doing. If you're doing something super simple, like, if you're trying to do x++ over and over, and let's assume the compiler doesn't actually optimize it away, which it would. But if you're just doing that over and over, you could probably do, more than 1 billion in a second. But usually the bottleneck for solutions are things like memory access instead. And so, in terms of like completely random RAM accesses, it's more like, something like some number of like small millions, like 10 million, something like that, instead of 1 billion. So it really depends on what type of operation you're doing. But yeah, because with this one, you're literally just operating on numbers in registers. There's no memory involved, and so it is faster. Okay, and people saying I missed the prefix sum part. Yeah, so one approach you can do on this problem is you can just kind of write the quadratic solution, where for every query you do a whole loop, and then once you have that solution, you can think about optimizing the sum part. But yeah, if you haven't seen the prefix sum thing, it is something to think about and learn, for sure. It's a very common idea. Yeah, and so so L equals R is a special case. So for that case, it's just a single element, and then you can just replace it with any number except the original number. So it's k minus 1. So I do have that as a special case. I think if I took that out, then I'm pretty sure I would get a wrong answer here. But yeah, you do have to watch out for that. And yeah, so basically the code ends up looking like this. Oh, Dush1729, thank you so much for the subscription. Yeah, Dush is actually also a server booster for my Discord server. So yeah, thanks so much for the extra support. Oh, now you have the AC emote. Nice. Okay, yeah, so just to wrap this up, basically, this is the difference of prefix sums, which gives us the range sum of the number of choices for everything that's not the left end or the right end of the subarray. This is the number for the left end of the subarray, and this is the number for the right end of the subarray, which is just what we were talking about here. So this formula, and this formula. I guess for consistency, I'll make it like this. Yeah, and so each query you end up doing an O of 1. Shoot, hang on a second. Okay. Yeah, so if you're looking for the rewind of the stream, if you joined late, you can just check out this link. The current stream will be in there, and you can watch any of the problems you're interested in. It should be the first one under recent broadcast. Yeah, so actually, if the range has just one element, that's a special case. But actually, if the range has 2 elements, that's not a special case. This will just be 0, and then we'll just handle the left end and the right end properly. Oh yeah, Max Wilson. I guess you got a little lucky if you didn't think about it and like make sure it worked. Okay. Anything going on here? Okay, looks like I passed everything, which is nice. I am still curious about my room. Okay, yeah, my room sucks for hacking. There's nothing really to do there. But okay, anyway, let's look at problem C. Okay, so problem C, you have this is probably called special, where a pair of positive integers a, b is called special if a divided by b floored equals a mod b. And then you're given 2 integers x and y. Find the number of special pairs a and b where a is between 1 and x and b is between 1 and y. And you actually have 100 test cases, and each one x and y are up to 10 to the 9th. So that's actually pretty big. You need to come up with something pretty efficient here. Yeah, so yeah, my room is not good, but I think I do think there were some hacks. Yeah, I was looking at this. I guess these were like at the very end. A couple people got these. So there were only 5 total, which is not a lot for, around with, something like around 10,000 people. But anyway, so for this problem, yeah, the first idea is like, let's try to analyze what special means. So basically, a divided by b, or like integer division, is equal to a mod b. And in other words, what that means is a equals br plus r, where r has to be less than b. Sorry. And also, we can also rewrite this as b plus 1 times r. And so, so this is, okay. And so this is basically what we're looking for. A and b work if a is divisible by b plus 1, and also a divided by b plus 1 is less than b. Sorry. Yeah, that's right. Okay. So in other words, it's at most b minus 1. Okay. So once you figure this out, then there are a couple strategies you can take from here. Oi Nishant, you should be able to rewind in the video and just pick where you want to start. So, so why is r minus b necessary? So r less than b. Why is r less than b necessary? So r less than b is necessary because if we just pick any other values, like let's say b equals 2, r equals 5, for example, then a equals b times b plus 1 times r, which is 3 times 5, which is 15, right? But if we actually think about a equals 15, b equals 2, then a mod b is equal to 1, which is fine. Well, actually, it's not fine because it's not 3, and then a divided by b is, 7. So these are not actually equal. The reason is because a mod b is just not equal to it's just not equal to r because r is too big. Hydrate. Yeah, so we do need r less than or equal to b minus 1. I Watch Coding said, these contests should not be free. All right, and some other stuff. But anyway, so yeah, so this is the condition we're looking for. And so essentially, we want to count the number of pairs where this is true and r is less than or equal to b minus 1. So yeah, there are a couple strategies here. We could choose, basically we can choose which of these to loop over. If we looped over a, then what would happen is we would need to factor a and then count all the factor pairs where the factors, like where x times y equals a, and let's say, assuming s is the smaller one, then we would need y minus x is at least 2, right? And so that's obviously too slow. I mean, we already have to loop up to 10 to the 9th and factor all of them, and there's no way you can do that. If we looped over b, and this is actually what I did in the contest, then basically the count of r is, it's the min of b minus 1, since r is at most b minus 1, and a divided by b plus 1. And so you can write a slow solution that looks like this, where I guess let's ignore this and look at this instead, where this is basically what I described. So we loop over all the b's, and then the count for r's is just the min of these two values, which is the same as here. Yeah, and then you could do some tricks to optimize this to take square root, square root 10 to the 9th time instead of 10 to the 9th. And that's what I ended up submitting. It looks like this, but it's not super clean. There's like a couple cases, and then you have to do this tricky thing where you find the largest number that has the same floor division as b. And I actually submitted a wrong answer for this problem first. It turns out the best way to do this is actually to loop over r. The reason for that is we know r is small because r is at most b minus 1, and a equals b plus 1 times r. So if you think about that, r can't be bigger than square root of a. Yeah, exactly, Nadeem Sheikh. That's the same idea. Yeah. Okay. So yeah, the idea then, if we loop over r, is that then in order for the r to work at all, we need r times r plus 2 is at most a, because we know that b plus 1 is at least r plus 2 based on this, right? And then b plus 1 times r has to be equal to a. So we can loop r from 1 up to, while this is true. And then the number of b's is just going to be a divided by r minus 1. So this is floor, because we know that b plus 1 times r equals a. So this is kind of the max b. And then also we have to remember that b is also going to be at most y. So this is the this is basically the limit on b. B can be anything from 1, given an r, b can be anything from 1 to this value. Yeah, and so the nice solution just looks like this. Just a super simple loop from 1 while this condition is true. And then, yeah, the min value for b is going to be r plus 1, since because of this, that's what we said. And then the max value is this, which is what we just described. And then we're just going to add the number of choices in that range. And then that's the answer. Yeah, so this is super simple, and it takes, I guess it takes square root of x time because of this loop. And so even if we do that 100 times, that's totally fine because it's not too big. It's basically 100 times square root of 189. So that's about 3 million loop iterations for a full test case. Yeah, so this isn't TLE because it's square root and not linear. But yeah, definitely a tricky problem. It feels, to me, it feels a bit too hard for a div2c, but I guess a lot of people did pull through and solve it by the end of the contest. And I think this is final. Oh, I can check out my final room standings. And yep, there was no chance of me getting any hacking points. So that would have been nice because it would have pushed me from 3rd to 1st. But I guess I should have just been faster. Mainly on C. Okay, so yeah, a couple more problems to get through. And it looks like, yeah, it looks like we can just keep going. So, okay, so problem D. Basically, you have a matrix A of positive integers, n rows and m columns, so up to 500 by 500. You need another matrix of positive integers, the same size, and then here are the conditions you need. The values need to be between 1 and 1 million. Bij has to be a multiple of Aij. And then if you look at any adjacent pair of cells, two cells that share the same side in B, the difference has to be, the absolute value of the difference has to be equal to k to the 4th for some integer k that's at least 1. It doesn't have to be the same for every pair. It's just for each pair it has to be basically some sort of 4th power. So this is kind of a weird description here, but yeah, this is what we're looking for. We can show the answer always exists. And so here's a key thing. The constraints on Aij are between 1 and 16. So very small numbers. And Nadim said k to the 4th may be very uncomfortable. Yeah, this is kind of weird looking. It seems kind of scary. That does seem kind of hard, but basically you kind of take the problem and break it down and see what you can do. And yeah, this is like completely just a thinking problem. It's like not really even a coding problem at all. The kind of the first thing to do is, okay, so one thing I noticed is any pair of cells that shares a side is going to have, if you color like a chessboard, so, you know, something like this, if you color like this, then any pair of adjacent cells is going to have opposite colors, right? Whether it's left, right, or up, down. And so I started thinking, okay, what if you assign all the white cells some number and you assign all the black cells some number? And that way you know that the difference between any adjacent pair is going to be the same thing. So I started thinking about that. And then, okay, so now you need to make, you need to pick a number that's divisible by everything from 1 to 16. Because if you're just going to do the same number everywhere, it has to hit all of these, right? And so one really important observation is if you look for the least common multiple of 1 through 16, it's actually just a bit under 1 million. It turns out it's actually this number. It's 720, 720. And this number is the smallest number divisible by everything from 1 to 16. And okay, so now we're in kind of a tricky situation because um, this number is just barely under our limit. We can't even double it without going over the limit. So, the only way we could make all the white cells the same number and make all the black cells the same number is if all the cells were this number. But then we have this problem where the difference is not k to the fourth for k at least 1, because the difference is just 0, and that's not good. So this is the part where you just kind of have to sit here and like think about it more and see out the problem. And what I eventually did was I picked one color. So let's say we pick white, and then we make all of the white cells the same number. We make all of them this number, right? So every white cell is 720, 720. And so all of those cover the multiple condition fine. And now we can just kind of solve every black square independently, which is nice. So when we solve this black square, whatever we do here doesn't affect this one, and it doesn't affect this one, and so on. Because for every black square, we're just trying to handle, given I have up to 4 neighbors that are all 720, 720, how do I pick the number for myself? So this seems like a good strategy, like a good approach, because it helps to sort of isolate each cell individually. And yeah, basically, if we think about it more, we can actually do something that's very simple. So we can take any black cell, right, and then look at the number that we need for it. So let's say we have a cell that wants let's say we have a cell that wants 13, right? So we want a number that is divisible by 13, and also the difference between it and 720, 720 is equal to k to the fourth for some k. So basically the clever idea is then let's just take the number 720, 720 minus 13 to the fourth. And that's the key idea. And it turns out this is fine because 16 to the fourth is still smaller than 720, 720. And so that's totally fine. And some people did minus, some people did plus, and either one totally works. Obviously, either way, the difference is 13 to the fourth. And so, yeah, the code ends up being super simple. You just, I have LCM right here. This is just a sanity check. And then you just read all of A. And basically, if I plus J mod 2 equals 0, which is one color, we just set it to that number. Otherwise, we set it to that number minus A to the fourth. Yeah, so that's basically all you need to do for this problem. I feel like this is almost the only approach actually as well, because at least I was reading the submissions in my room. They all did something like this. The only kind of variation was people, I'm not sure who, I think this was, no, sorry, wrong problem. D. There were a couple people who had like pre-computed arrays. That was the only main variation from this idea that I saw. Maybe we'll find, yeah, for example, something like this. And so I was wondering a bit about this, but it turns out if you kind of just take this number and you look at, this difference. Oh, I should import math. So math.pal to the power of 0.25. Then yeah, this is just, this number minus 28 to the fourth. And so a lot of people did this idea and they just pre-computed a number for each value 1 through 16. But it's kind of funny because they basically took this and they tried subtracting, k to the fourth for every k and decided, oh, the result is divisible by this, so I'll make it a solution for that. But you can just make it even simpler and just subtract, a to the fourth, and then you're good. Oh, hydrate. What if there was a condition that the sum of all the elements has to be the minimum possible? So, that one, I'm not sure that'll have a very fast solution. Yeah, that feels like definitely a much tougher problem because you can't just do something like this where you kind of ignore half of the squares, right? You have to really optimize everything, and so yeah, I think that is a much tougher problem. I don't think it will have a fast enough solution. Okay. Cool. So we have two more problems to talk about. E and F. I might actually talk about F first, since it has more solves. So a lot of people did find it easier than E. Yeah, so let's talk about F first. Okay, so you're given an array of integers b1 through bn, and then you're given that an array a1 through an of integers is hybrid if for each I at least one of these conditions is true. Either bi equals ai, or bi is the sum, a1 plus a2 plus all the way to ai. The funny thing is for I equals 1, those are the same. And otherwise it depends on the array. Like these are basically these are two conditions. We have to satisfy at least one of them. We can satisfy both, and that's fine. And we just want to find the number of hybrid arrays a1 through an and put that modulo this value, which is kind of a very common mod. It's a prime. And so yeah, n is up to 2 times 10 to the 5th. And then notice that bi can be negative as well. So they can be between negative 10 to the 9th and 10 to the 9th. Okay, so basically for this problem, you can already think of a pretty easy brute force 2 to the n solution. And that's just essentially for this, you decide which of the two you're going to satisfy. And then once you've decided, one of these two for every I, then you have a unique choice for AI, right? Because each equation tells you what to do for that AI. Like we already know A1 equals B1. And then for A2, either we pick this, and so A2 equals B2, or we pick this, which is either A2 equals B2 or B2 is equal to A1 plus A2, which means A2 is equal to B2 minus A1. I guess we'll just... And so we can solve for A2 and then so on. And yeah, so we could just loop 2 to the n and try all of them. The one thing that's a little tricky is we have to make sure that when we're counting it, it's actually new, it's actually unique. So we could just do that by storing all of the arrays into a set or something like that. But obviously that's too slow, so we want to do something faster here. And yeah, the key idea is that this is kind of the more interesting condition than this. And so if we look at an array where, let's say we have indices, we have 1, and then up to j, and then we have some more indices, and we have up to I. And let's say that j and I are kind of two closest indices where they both picked this one. So in other words, bj is equal to a1 plus aj, and then bi is equal to a1 plus ai. But in the middle, for example, bj plus 1 equals a j plus 1, and then b, I minus 1 is equal to a I minus 1. Yeah, so let's say between between j and I, everything picked this version, and then j and I picked the bottom condition. So then what we know is that, well, basically AI is going to be equal to well, first we can write this. So let's try to figure out what AI is equal to. And then this is just And so this part is going to be bj. And then, for example, aj plus 1 is just bj plus 1 because of what we know above. And then plus bi minus 1. Finally, plus ai equals bi. So we actually know exactly what ai should be. And it's just bi minus all of these other b's. And that way we can kind of do this sort of DP on, the DP is essentially on, here's a prefix, and the last thing in the prefix picked the second condition. And now the one thing to be careful about is, what if the second condition gives the same AI as the first condition? Well, then in that case, we shouldn't allow picking this index, basically, because we could just skip this index and it would get the same result. So we should only allow like a DP state on this position when picking this condition resulted in a different AI than BI. So that idea, it's a little bit tricky, but the key thing there is we're trying not to overcount the cases where this condition and this condition give the same number. So we're especially counting the cases where this condition results in a different number from this one. And so then we can write up this pretty easy quadratic solution. Looks like this. Basically, you read all the b's, and then I do this prefix sums on b because we need to like compute this. And then we have a DP state. So DPI basically means for the prefix ending at I, if I satisfies this condition, and not this condition, what is the number of A1 through AI we can pick? And 0 is kind of a special case. We set DP0 to 1, even though it satisfies both conditions. It's just the only special case, just to kind of base case our DP. And then basically, we just do this idea where DPI is going to be the sum of everything except the cases where this sum is equal to 0. Because if this sum is equal to 0, then AI is just equal to BI based on this formula. And that violates the condition we said about not satisfying the first condition. So how do we know when this is 0? Well, this is just 0 when the two prefix sums are equal. So also sum over j where bj plus bi minus 1 equals 0 of dpj. So we got to subtract those out. We got to exclude those. And so that's basically what we do here. We just take the full sum, we loop over all the j's, and if b sum I minus b sum j is 0, then we just subtract out dpj. And yeah, the final answer is dp sum. It's just the sum over every index of like, what if this is the last index where we do this, right? And then everything after that, we'll just do this. And so this is a really simple quadratic solution. This is a correct solution. And so now, obviously n is up to 2 times 10 to the 5th. We don't want to do quadratic. We need to do something a little faster. And hydrate. Okay, so what do we do? Well, this is actually super simple, right? This is like one of the simplest DP loops ever. Not that the idea is simple, just that the code is simple, right? So we're just trying to subtract out the sum of all the j's, dpj's, where b sum j equals b sum I, right? So yeah, the only optimization we need, we just keep a map of the sum of dp's based on the b sum. So in my actual solution, I have something where, yeah, I call it a map, and then I call it b sum dp. So it's just the dp sum based on the same b sum. And so now it just looks like this. You just take dp sum, and instead of doing this loop right here, you just go through and you subtract, or you just do one lookup, you subtract b sum dp of b sum I, and then you update b sum dp of b sum I. and then the answer is still a TP sub. So yeah, very simple code. The key idea is to understand the TP state. So maybe I'll just like write it out here one more time. The number of choices for A1 through AI, given that AI satisfies the second condition and not the first condition. Where I equals 1 is a special case where it is allowed to satisfy both. And that's the key idea. Yeah, I definitely agree that giving hints so people can keep trying is nice. I'm not sure if it makes as much sense in terms of like my stream, where you know, if you're watching it, then you're hearing the hint, but then you're just immediately hearing the rest of the solution right after. But yeah, if that's something you're interested in, you could also, you know, you can check out the hints and think about it more, and then you can also check out the Twitch VODs later. Oh, my library. So I still need to do that. I still need to like upload it to GitHub, so it's not there yet. Yeah, I generally also upload my streams to YouTube, so you can find my channel there. Okay, so we have one more problem, and I do need to get going pretty soon, so I'll try to go through this reasonably quickly, and then we can kind of wrap it up for today. Oh, Mango lastly did F differently. So then how do you turn that into like a fast enough solution? Sure, yeah, you can post your submission. Yeah, I'm not. I'm still not sure I get the idea. It sounds like, oh, that's funny. It's more similar to the official solution than mine, maybe. Yeah, I guess I'll have to take a look later and try to understand it. But okay, we do need to. I have about a little under 15 minutes, so do need to go through E. So let's try to do that. Yeah, so E, basically, you're given a tree. Your tree has n vertices. It's rooted at vertex 1. And the leaves are all the same distance from the root, which is important. And then you're given n minus 1 integers, a2 through an. And basically, this is all basic stuff. And then basically you have this situation, this game where you start with a red coin and a blue coin, both on vertex 1. And you make D moves. You start from the root of the tree, and then you go down all the way to the leaves. There are 3 things you can do in your move, or 3 things you do, like you must do. The first one is move your red coin to any child of where it currently is, and then you move the blue coin to any vertex B prime such that the distance from 1 to B prime is 1 greater than the distance from 1 to B. So basically, this just means that you can move it to any vertex in the next level, like the next layer of the tree. And it doesn't have to be connected. It doesn't have to be a child. You can just pick anything. And then you have the choice of, you can swap the 2 coins or you can skip that. And they can be equal at any time. There's no number on the root. This isn't super important. I mean, you can just pretend there's a 0 there or whatever. And after each move, you gain the absolute difference between AR minus AB points. So you want to know the maximum number of points you can gain. And it is pretty big, up to 2 times 10 to the 5th. AI are also pretty big, 10 to the 9th. So, okay, so yeah, basically, we're kind of trying to find the best strategy, like the best scoring strategy for going from the top to the bottom. And to try to summarize this, we can kind of we have 2 nodes at each level, and then what we do, a simplification is we have 2 nodes at each level, and then what we do when we go to the next level is one of the 2 nodes has to go to a child, and then the other of the 2 nodes can go to anything. And that kind of encapsulates the fact that we can swap or not swap, and then the red coin always has to go to a child. So instead of red and blue and swapping, we can just throw out the swapping and just say one of the coins has to go to a child, and then the other coin can go anywhere. Okay, so given that, we have kind of an idea where we have a common DP idea where, let's say we know which 2 nodes on the current level we're at, then we should just maximize the score so far, right? And in fact, because of the fact that one of the 2 vertices can go anywhere, we don't even actually care where that one is. We only care where the one that has to go to a child is. So we can have a DP state where it's basically a DP on a single node in the layer, which means given that this is the node that has to go to a child on the next move, what's the best score we can get? Maybe I can pull out a drawing tablet real quick. Okay, we're gonna have to kind of speed run this explanation today. Okay, here we go. Cool, just setting up a Jamboard. Okay, here we go. Is this actually on? Okay, let me just make sure. Okay, that's good. Yeah, so basically we have a tree, we have a couple of different layers. And at each point, basically what I'm saying is the DP state is, let's say the red one is here and the blue one is here. We don't actually care where the blue one is because the red one is the only one that's constrained for going down. So if we know the red one is here, then the next red one has to be here or here. The blue one can go anywhere, right? And so, even if we had another, the blue one can go anywhere, the red one has to go to one of these 2. So our DP state is just given a node, what's the best we can do from the beginning to that node. Oh, that's true, 701. Okay. Yeah, so that's the DP state. So that's nice because the DP state is just 1 state per node. And then what we can do is we can think about a quadratic solution where, given that we have we have red at this node, we can now iterate over all the children. Those are all the options for the next red. And then based on those options, we can iterate over all the blue for the whole layer and then update the state based on that. The other thing we can do is we can factor in swapping red and blue and update based on that. And so this is a quadratic solution because it's basically for each pair of layers, it's like number of nodes in this layer times number of nodes in this layer. is the runtime, and that ends up being quadratic. And to optimize it, you basically do a couple of different optimizations here. So yeah, first we just read the tree, we set up the levels. So we're just doing a DFS and tracking the depth. We put everything in the same depth into a level. Read the AI. Yeah, and so this is the DP state we described. And yeah, there's basically a couple things we need to do to optimize the transitions at a level. So the easier part is actually going from one level to the next level. In that case, we just go from each node in the level to each child and just do this, where the child is just taking the DP of the node, and we haven't yet contributed how much extra score we get at the child's level. That's what we do here. So we're doing a transition between the nodes at D, right? And here, basically we have two options. When we bring the red down, so let's say we bring down to here, right? Oh, that's like not. Hopefully it's clear this is R and this is B. Kind of overlaps the node, so it's not super clear. But anyway, if we take red from here to here, and if we decide not to swap, right? Then we just take the best B, right? And the best B is either, because we want the max absolute difference, the best B is either the smallest thing in the level or the biggest thing in the level. And those are the only two options. So that's a pretty simple case. I handle that here, basically taking minimum and maximum, the smallest thing and the biggest thing. And then those are these two options. So either do DP node plus maximum minus A node, or DP node plus A node minus minimum. And that's the case where we don't swap. And now the case where we do swap is more complicated. So in that case, what we're doing is like, essentially, instead of, let's say this is B, and we swap this B and R, so they actually become R and B, right? Well, in that case, we can kind of think about it as, okay, this R state, like the R state from here, is actually coming from the R state from here, right? Because everything before this, we operated as if this were the R, and now we're swapping these. So essentially, we have an idea where we take the DP value here, and then we add the difference between these two. So it's they're kind of two cases. One case is for nodes that are bigger than this node's value. We'll just take we just want to maximize DP of the other node plus the value of the other node, because we end up wanting to maximize. Let's say, okay, let's call this node X, and then let's call like this node Y. We're trying to maximize DPX. Then it's essentially like DPX. I can actually just type this one. That's probably better. Okay, so it's essentially DPX equals max over Y, where AY is greater than AX of DPY plus AY minus AX. Okay, and I will stretch this out. Okay, and that is the case for AY bigger. And so then you notice, because AX is fixed, we can just extract out this DPY plus AY term and just maximize that. And then the other case is very similar. It's just if AY is less than AX, then we want to do this instead, right? Because that does the correct absolute value. And so now we just want to maximize DPY minus AY. Okay, and so actually I realize now that what I did is, I think it's more complicated than necessary. Yeah, it's more complicated than necessary. What I actually did is I got all these choices. So one of the choices is like this is basically dp of the node minus a of the node. This is dp of the node plus a of the node. And so you end up wanting to take a suffix max of these, of the plus, and then a prefix max of the minus, right? And so I made a prefix max array and a suffix max array to get those. And then for each node, based on its A, you can binary search this sorted choices array, and you have the option of the prefix max at that index or the suffix max at that index. And for the prefix max, because we're doing minus AY, we want to do plus AX. For the suffix max, because we're doing plus AY, we want to do minus AX. But I think you can just ignore the prefix suffix thing, and you can just do the max over all Y for both of these. So I think you can actually just remove this condition entirely and just do max Y. The reason being that, if AY is greater than AX, then, this one will definitely be better than this one. And so even though there's like kind of an invalid value here, it won't actually affect the result because this one will be better. Yeah, so that can help simplify the code. But either way, it's fast enough. I guess the difference is my solution, like what I submitted is n log n, but if you do this idea, you can just get it to O of n. But either way, it's definitely fast enough, and it's just like a nice little DP problem. Yeah, so yeah, in terms of implementation, just a couple different things. Yeah, you DFS, get the levels, and then I personally found it helpful to like separate out the D to D+1 transition and then the within D transition. And this line is a little too long, actually, but it would be better, like, just kind of logic-wise, to separate out this minimum maximum part from the prefix suffix max part. But I just kind of like threw this in quickly at the end, so it's all kind of bunched together. But okay, yep, that's it for this contest. I do need to go. I have something in 2 minutes, so I will call it a day for the stream. And yeah, thanks everyone for coming and checking it out. Be sure to follow the channel for future stream notifications. And also, I don't think I mentioned, but I have a Discord server, and yeah, if you want to just join the community, you can do that too. And here's a link. So there, I don't know who this person is, Neil Wu H, but they're definitely an imposter. So maybe they'll tell us who they are, but I don't know. I don't know if we can trust what they say. But anyway, that's it for now. So okay, see everyone next time.